Page 192, number 37. X to the 2/3 minus 3. And the directions say, find the relative extrema using the second derivative test. Okay, so a little bit of side note, backtrack, big picture here. You may not want to write this down, but one more time. Start with the critical points. Those tell us the possible extrema. And then we have options. That's probably the neatest. I've drawn that little pitchfork looking thing. If we do a table, we get the absolute extrema. Remember to include endpoints. We can do the first derivative test. That's intervals, number line, etc. That gives us the relative extrema. What this problem asks us to do is the second derivative test. So evaluate the second derivative at the critical points, because then we're thinking concave up versus concave down, and we can get the relative extrema that way. So if it didn't specify, we could have done this using the first derivative test, using the increasing, decreasing thing, like number 2 on the warm-ups. But it specified, find the relative extrema using the second derivative test. So that's the direction we're headed. First derivative, 2/3 x to the negative 1/3. The minus 3 goes away. I do need a second derivative, but I also need critical points. So I have to pause my thinking here for derivatives and set this thing equal to 0 to figure out what my critical points are. And then I'll find the second derivative and go from there. So let's see, that's 2 over 3 cube root of x. So that's equal to 0 nowhere, because there's no value that would make the top be 0, so that doesn't really apply. But it's undefined when the bottom is 0. So x equals 0 is my critical point. That means it's a possible extrema. And so now I'll have to worry about it for second derivative test. Well, second derivative test requires the second derivative. So same process. It's still a polynomial, or not a polynomial, it's a power. So 2/3 times negative 1/3 times x to the negative 4/3. So let's see, that would be negative 2/9 and x to the 4/3 in the bottom because of the negative. All right, big picture over here. So we've got a possible extrema. We want to test it into the second derivative to see if it's concave up or concave down. So at x equals 0, f double prime of 0 is negative 2 over 9 times 0. Uh-oh. Undefined. So that was cruel of them to tell us to use the second derivative test when the second derivative test does not help. So I'm not sure what it wants us to do, to just say we can't do it, or if it wants us to back up and try the first derivative test. So second derivative test for this problem doesn't work. Let's back up and try the first derivative test. Which is, again, I'm not sure it wants us to just stop and say you can't do it, or if it wants us to go to another method and check and see. So first derivative test, I'm going to plug it into the first derivative. And I'm curious about increasing and decreasing. So f prime was 2 over 3 cube root of x. So if I plug in -1, I get negative, whatever it is. That means f is decreasing. If I plug in 1, I get 2/3, which is positive. F prime is positive, that means f is increasing. And so by the first derivative test, I know that x equals 0 is a minimum, because f prime changes negative to positive. Relative minimum. I kind of don't like that question because it explicitly it tells you a method to use that doesn't work, which I guess on one hand illustrates that sometimes one method works when the other doesn't. You want to check the back of the book and see if it works using the other method like we did, or if it just throws up its hands and said you can't do that. 192, number 37. Yep, it says there's a relative minimum there. So we agree, but it's not by the second derivative test, because their second derivative doesn't work there. And the reason is, if we graph this, it looks something like that. So there's a minimum there, but because it's a cusp, the first derivative doesn't exist. And if the first derivative doesn't exist, you can't get any further derivatives out of it. Good question. Tricky question.